Hi everybody. Today we're covering the kind of the back half of chapter 3, which if you remember, we've just come from the end of a longer break, so we're kind of getting back into the basics again. And so last time I think we mostly covered like single predictor linear regression, and so now we're kind of getting into the multi predictor stuff. And I guess maybe the next slide.
Oh, sorry, I've got some pop-ups to get through.
Sorry, I know
there you
it's yeah, and so there's a lot in the last part of this chapter, and so I guess we probably won't hit everything in great detail, especially since I've caused us to start late. But I saw in the chat over the break there was like some interest in the kind of multivariate, like the equations and proofs for multivariate OLS. So I thought we'd start with that, just since there seemed to be some appetite for that. I think Jack posted a link, and it also like I think will help kind of conceptualize the rest of the the discussion. So maybe that's a good place to start. So yeah, the next slide, I guess. Sorry, Jack, I feel bad.
No, good.
Okay. Yeah, so I think, if you, this is the equation for beta for in the sort of multivariate OLS setup. And so this is the linear algebra, like the matrix formulation. And I do think this is one of those few cases where I find the matrix formulation a lot easier to understand than the sort of like single unit formulation. But so in this case, beta is like actually like a column vector of all the different predictor parameters that you have in your model. So you'll have like usually like an intercept and then beta 1, and then however many predictors that you have in the model is how many will be in beta. And so the question is like, how did we get from what we know about OLS to this estimator for beta? And then that's on the next slide.
Do you want to check? Okay.
Oh, yeah. And so I don't go through it in like full detail here. And this is probably like the limits of my linear algebra skills is probably this, solving for beta here. But so you start with the residual sum of squares, which we know is just kind of like the squared y minus the estimate of y. And then when I think the next slide maybe has, yep. And so we want to minimize that. And so to do that, we take the first derivative. And when we set that first derivative to 0, we can solve for beta. And so I think the way that works is you multiply both sides by x transpose x, and then that turns into the identity matrix on the left side, and then you end up with that original equation, the x transpose x y or whatever the equation is. And so to do that, you have to have x transpose x has to be invertible, which usually isn't, usually is not a problem. I think if you, and maybe, I don't know, does anyone else know what situations where you would have a non-invertible matrix like, sorry?
Actually, I believe that is the main point is to find it invertible, because anytime you have any collinearity, it won't be invertible.
Okay. So collinearity. Okay, right. Okay. Yep, that makes sense. Oh yeah. So yeah, you need to have no right. Yeah. No. Your collinearity can't be too bad, at least. Okay. So the next slide. I think this just shows the formulas for variance. I didn't do the proofs for these ones because they're kind of hard, at least to my my eye. And so for the multivariate case, variance is kind of like expressed as a square matrix. And so the way we calculate that is by oh, and I'm sorry, there's a mistake. This first sigma should have a hat on it. But yeah, so the way we calculate that is by multiplying the sigma hat, which is an estimate of the variance, which we were estimating from the residuals. So yeah, that's right. So and then just multiplying it by that x transpose x inverse. But yeah, that's the key thing, is we're kind of estimating the single kind of single homoscedastic variance from the residuals of the model. But it's an estimate, not like the true variance. And I think the next slide just shows like what a covariance matrix looks like. Oh, sorry. Now we've got hats. Well, I think it's fine.
Yeah, I got to clear them all.
Okay.
I'm a bit of a boomer here with this stuff.
Yeah, and so the important thing to know about this covariance matrix is that obviously, like on the sides, you have the covariance between each parameter estimate, and then the diagonal gives you the variance, which is kind of like usually what you want. And so then on the next slide, I think. Oh, okay. So again, I think Jack was talking about like, oh, like can we implement this? Using, I think you're using MLX, but I just thought like, okay, could we do this in NumPy? And yeah, you could pretty easily. And I haven't double checked this, but so just using NumPy's matrix inversion function, you can calculate beta. And then on the next slide, we have the variance. And yeah, the key point with the variance, I think, can you scroll? Does this scroll this little? Okay, yeah. Is that once you get the covariance matrix, you want to take the diagonal. So I guess NumPy has a diagonal function, and then you can subset to get whichever parameter you're interested in. So that's kind of like the from the ground up version, a little bit more of multivariate regression. I know, like usually, I think we just kind of plug everything in and let it rip. But it seemed like there was some interest in like exploring that proof and that how to implement it. And because it is like simple enough that we can look through it relatively easily. I don't know if anyone has any like thoughts or feelings about it.
I'll just start. You're asking about invertible matrices. There is a invertible matrix theorem, which gives you like 10 conditions that are equivalent for whether a matrix will be invertible or not.
Oh, okay.
Yeah, and finding the inverse numerically can be quite a difficult problem, especially as your matrices get big. It depends on, it's called the condition of the matrix, which is how I think it's something to do with the ratio between the biggest and the smallest eigenvalues, something like that. But yeah, I realized that there's quite like a theoretical linear algebra answer to your question of when will this break, rather than when does this happen in practice in statistics, for which Sandrine's answer was much better. Yeah,
and my understanding is that inverting, like matrix inversion, is one of the like kind of like computational bottlenecks of like a lot of like basically anything that is doing linear algebra, because it's so hard. But yeah,
it's kind of worth doing some by hand, like taking a 2x2 matrix or a 3x3 matrix, getting the identity matrix, and then it's like, I literally haven't done it for years, but I think you try to get into reduced echelon form now. So you do a bunch of operations and you track on the identity matrix what transformations you had to do to your matrix, and then at the end you have it. But you can do it on like a 2x2 or 3x3 matrix, like by hand, to get an intuition for like what's a matrix really, like some transformations through things, and why does the identity stuff matter, and like why does the inverse matter. And it's definitely doable if you sit down with a tutorial or like a textbook, and I kind of recommend it.
That's an absolute throwback, that row reduced echelon form. That's bringing back horrible memories of university. Doing that by hand.
Just the 2x2 matrix is like, I think it's like pretty painful to do by hand. Like, I feel like I'm, have to like, have my textbook open and I have to go, it takes quite a while. Yeah. Okay. Well, so that's that. So that's just kind of the, grassroots, I guess, of this adventure. But yeah, so I think the next thing, and I guess next slide.
Oh, I just
Oh.
say as well, you mentioned the MLX thing. Like
Mhm.
what I've been doing is I've been doing like the variance, covariance, and all this, and then the regressions. And because MLX is so similar to NumPy, like it's basically like a NumPy API, but it's like only slightly different. So it's really like not very different to this. So if anyone is interested, you can do it basically with NumPy code. But
Is MLX like a for like the Apple M series? Is that what it is, or what? Okay, and it's like accelerated on. Okay, interesting.
It's all it's like, so you have CUDA for NVIDIA. It's like
right. Okay.
Really fast parallel computing for like acceleration. MLX is like built for metal, like metal plated silicon that Apple uses now. And yeah, it's like newish, so it's still being developed, but it's pretty fast. Like GPUs do go bro when you use it.
Yeah, well, that's very cool. Yeah, so I guess the next little section is about in the multivariate case, especially like how we can tell if we have whether or not our predictors are good predictors, whether or not they're significant, whether or not they like add anything basically to our understanding of the model. And so the way the textbook, kind of the main tool we have to deal with this in this chapter is this F statistic. And so, intuitively, I think we're asking like whether or not our model taken as a whole is kind of significant or sort of adding to our understanding of the outcome. So in terms of hypothesis testing, our null hypothesis is that all the betas are jointly equal to 0. So beta 1, beta 2, so not that, just one of them is equal to 0, but all of them are equal to 0. And I think the next slide has like a thing about intuition is the, so I had this first just to help us remember the formula for residual sum of squares. And I think on the next slide is the TSS. The TSS is kind of the proportion of the variance in Y explained by some predictor X, or in this case, like set of predictors. And then on the next slide, and maybe
it's in TSS is like, so it's like the real values minus the mean, so Y bar.
Right. Yeah.
And then you've got your other formula for the predictors, which maybe I skipped over.
Wait, which one are you looking for? The no, I don't have I think I only have the one, but I know what you're talking about. Like if you substitute, you can do some substitution to get, I think later on maybe I have the full, I'm not sure, but yeah, there is another formula for TSS.
Well, because it's in the variance of the data, you're looking at the average being like the least biased estimate, like or zero bias, and then that's like the actual data minus the mean of Y, like that's like variance in the data. But then you've got separately like your estimates minus the true values minus the estimates, and that's like and then you do the division and you've got the amount of variance that you are accounting for over the total.
That makes sense. Like when you think of Y bar is kind of like a baseline estimate. And I guess I have a question. Like I was trying to explain the intuition, just kind of, myself, and I kind of explained that formula as like dividing the explained variance, which is like kind of TSS minus RSS. It's like the total explained minus the kind of like the residual part, like the unexplained part, and then dividing by the level of uncertainty, which is kind of captured by sigma squared. I don't know if that's just my kind of gloss on that. So I don't know if other people agree with it or maybe have a different interpretation, but I was kind of trying to motivate that. But yeah, I think the key thing is that, we have this kind of explanation of how much of you know, some percentage of variance that we've explained, and then some measure of uncertainty, which is I think kind of captured by sigma, sigma squared. But in any case, you want like big F values. So like if your F value is close to 1, then your kind of explained variance and unexplained variance are pretty close together, I think, intuitively. They're like quite, you know, they're similar in magnitude. And I think, as we saw with the formula, just like with p-values, if you have a really high number of observations, that can influence the significance of the F test. So if you have a really high number of observations, you're more likely to get a significant value, even if the actual number is quite small. So yeah, I would be interested to, because you know, I didn't feel like I grasped that like as well as I wanted to, but that, yeah, that was kind of my gloss on it. Yeah, I don't know. I think it's fine. So yeah, I think the next slide, unless anyone has any thoughts.
Sorry, I can't see Zoom and thing at the same time, so I'm often switching between the Zoom to check if people are about to speak or not before switching.
Oh, sorry.
Did anyone want to add anything, or should I carry on?
I guess
Going into the highest bidder, yeah.
Oh wait, is there a chat, or did I just miss this earlier chat? Oh no, okay. This was the earlier chat about the book package using the NumPy inversion, I guess. I think that's what that says.
I think it's possibly highlighting this p-inv, which is probably the pseudo inverse. So the inverse is only defined for matrices.
Okay.
And it might also work for actually X transpose X, to be honest with you.
Yeah, because it's always MN and N, so it should, yeah. Yeah, so why do they use the pseudo? Because that extends, you can invert non-invertible matrices now with the n-row stuff, but what's the,
is it faster?
Why is that in there?
Is it like kind of an approximation where it's a little bit faster, maybe? That's just a guess.
Yeah, it should be longer because you're changing the shape now with this. You're adding stuff. You know, it's like broadcasting stuff to the bottom of one if it's not meeting the shape of the other. But I guess Tom's point, yeah, it's like you've got the predictor matrix X. It's like has m columns, has n. Sorry, it's n and n times n. So yeah, it's got like m rows, n columns, and then when you transpose it, it's got n rows, m columns. So they have to, the shapes have to like match up. But then I guess it can be rectangular. Is it like making it square or something? Like, does it help if you make it square?
I think it'll be more robust for badly conditioned matrices than trying to do the straight inverse, potentially.
Yeah, that's the exercise was left to the reader. I was maybe thinking with the F statistic. But yeah, it's a bit funny. I wonder if it's actually worth just calculating some in an ID, just seeing how the values change when you change some of the parameters. Because it's pretty similar to R squared, but it's not, because it's got stuff about the parameters and stuff in it. But it's as well, I don't know, does anyone know, do they correlate R squared and the F statistic, or are there times when like your R squared might be very high but your F statistic very low?
That's a good question. Yeah, I mean, I'm trying to imagine. Say you just like arbitrarily keep adding predictors, your R squared will continue to get higher. I guess the F statistic I think has an adjustment for the number of predictors, doesn't it? So but yeah, I think they must, like, I can't imagine them going in opposite directions. Yeah, so I don't know. Yeah, that's a good question.
I have a feeling they can. I don't have that much more information on that opinion,
Yeah.
but I think that they can go. I don't think they have to correlate. I'm open to correction on that. Like it's like a memory, not a.
Yeah, it seems I have that like feeling that it's like, there's like that's like one of the like pitfalls or something. You're like, they don't have to correlate. But yeah, I can't think of how you would do that.
There's an n in the denominator. F is there for R squared? I don't think there's not for R squared, is there?
It's just that what I remember about the F testing when I was taught about that is that it's more useful to test it nested model. So basically, it's more to check out if a bigger model is better than the smaller model. So it's more how I always have understood it, not like that, but more on just testing nested model.
And I actually think that might be the next slide. Is the use of to test a subsetted model against this is just the if you want to get the F statistic, you can get it from the object that's returned by model.fit in this in the books package. And I presume maybe probably most linear regression packages are going to return it. But then I think the next slide is the one that has this so this if you want to calculate the F statistic for a subset of predictors, you can do that to do what Sandrine just like described, where you're basically comparing a more limited model to like I think they call them like fully saturated models. Is that right? Where you have like a model with lots of predictors versus a model with fewer. And then you calculate the residual sum of squares for this model that has the fewer predictors, and then use that to calculate the F statistic. And I think what's going on there is it's basically substituting the TSS of the big model for the residual sum of squares for the little model, and then the residual sum of squares for the big model for the the residual sum of squares in the original formula. Sorry, I didn't explain that very well, but basically you're just kind of changing the numerator and the denominator of the original formula, where you instead of comparing your one model against the total kind of variance, you're comparing the smaller model against the bigger model. And then the textbook kind of gestures at these like maybe more algorithmic ways to approach this problem. So like if you so this is like not really feasible to carry out for if you have like any reasonable number of predictors. Even if you have like 5 predictors, you end up with like a lot of different permutations of different models that you have to kind of horse race against each other with the F statistic. And so the book kind of gestures at these other ways of figuring this stuff out. And so I actually had never heard of these. I don't know if anyone else has worked with these before, but yeah, so like with forward selection, you kind of like continue to add to the model until the predictors aren't sort of adding new information. With backward selection, you like subtract from the model until the subtractions aren't losing information. Is that right? Oh no, when all the remaining variables have a p-value that is sort of at some, arbitrary threshold, and then mix, I guess, is like a mix of the two where you kind of go back and forth to. But so I've never really used that either of those approaches, but they sounded interesting.
Yeah, there will be it's chapter 6.
Okay, yep, chapter 6.
In the chapter 6, they are going to explain everything about that.
Okay, that's good. Yeah, it sounded, yeah, no, I guess I'll leave it at that. Yep, that sounded interesting. Okay, so the next.
The book does also say, I was just rereading the book to slightly tweak something in my memory, but the book also says that when the number of predictors is too high, like you can't use the least squares methods, then you can't use the F statistic anyway. So like basically don't worry about it. And in chapter 6, we're going to talk about some of these methods.
Okay, yeah. Yeah, and so just to go touch on this note about R squared in the multivariate context. I think we talked about R squared at the last session, but yeah, so in this context, and I guess we just kind of have said this in the last couple minutes, but R squared isn't adjusted for the number of predictors, and so it will like continue to grow as you add predictors, even if the predictors aren't kind of adding substantively to the model. So it kind of has diminished usefulness in this multiple regression context. So the what is RSE residual? I'm forgetting what the acronym stands for, but this other measure is kind of superior in this context because it has, as you can see in the equation, has the adjustment for the number of predictors. What is it?
But it's a root something error.
Oh,
no?
root squared error. Root squared.
It's not
whatever.
RMSE. Like it's not.
No, it's not RMSE. Yeah, that's mean squared error.
Yeah.
Oh, okay.
Okay, residual.
But yeah, I mean, I guess, maybe residual standard error makes sense because it is just the residual sum of squares and then kind of standardized, I guess, by the number of predictors and the number of observations. Yeah. Yeah, I guess next slide, unless anyone has any.
So just looking at the formula, like, so as you get more predictors, like the number that's multiplying RSS is getting like smaller. So or is it the other way around?
So let's see. So as you get more predictors, RSS or RSE should get yeah, let's see. RSS gets smaller. So RSE gets smaller. Yeah. So yeah, I think that's right. I think you want a large RSE, and then as you get more predictors, RSS, therefore RS, or the quantity under the square root gets smaller, and therefore RSE gets smaller. Is that right?
Sorry, I was going to ask, is this the same as the adjusted R squared? So the output of the ordinary squares model, one of the metrics is the adjusted R squared, which I think might be this, but I don't know the formula for that off the top of my head.
Yeah, that's a good question. I actually don't know that either. But yeah, I'm aware that there is like an adjusted R squared. So yeah, maybe this is just that.
But yeah, I think RSE gets smaller as predictors get bigger.
I'm going to write that down because I want to know that too.
The adjusted R squared. Did they go over that? I remember them.
I don't think they, and so maybe this is
no,
just their terminology for that same quantity, but
what I would say is I don't think you come across this RSE very often. Like I don't recall ever actually like seeing this in the wild or anything. I don't know if other people have, but I definitely have never used it myself.
No.
Yeah, I've used adjusted or squared, but not RSE. So if they're the same thing, I have used this.
Yeah, I'm Googling for the
And
let's
I
see.
think it is. I think it is.
I get a bit in the book where they introduce this.
Yeah, so I'm looking at, the formula for adjusted R squared uses R squared instead of RSS, so I can't like do the simple algebra in my head, but yeah, it looks similar enough that I feel like they are the same thing. At least from my, cursory Googling.
I wonder, is that more correlated with the F statistic, so than R squared itself?
Yeah, I'm trying to think. Because I mean, this one has the adjustment for the predictors, so I can't think of any other way that they could like diverge. Yeah, I think you're probably. I mean, I think that's probably true.
Nice.
Yeah, I'm looking at it, it doesn't look like they're the same. Unless
I'll
no, let's stick a thing in it and come back to it and have a little look after the thing, because I feel like we won't solve this here. It would be too much to take the adjusted R squared formula now and see if you can get this.
Yeah,
I don't see that you could, but maybe you could.
they look similar, yeah, but I'm not sure that I can't tell if they're identical or not. But yeah, maybe that will also be an exercise for the reader. Okay. Oh, my picture has broken. Maybe that's a consequence of the
yeah, because it's a zip.
Sorry, I was hoping that it would go with the files, but I guess maybe my file paths or something weren't relative enough or something.
Do you know which cell output it is? Because then I can get it from the files probably.
It is. I know the figure is just figure 3.9. I don't think I had it in a cell. I think I just did it with Markdown. But yeah, so yeah, sorry everybody. Well, this is silly. But yeah, so I don't know. Figure 3.9 is just kind of a figure demonstrating like what happens to your residuals when you have like a nonlinear trend in your data. So this is, and I wanted to have like a little bit more like meaty mathy exploration of these kind of assumption violations, but I kind of ran out of time. So, but like intuitively, if you have nonlinear data, then your model isn't fitting the data well. And so one way to explore that is to use a plot of the residuals. And I think they gave us some. Oh, sorry.
I'm just going to get into just open the book to share because you said.
Okay. Yeah. I think that's better, honestly. Yep. Yep. So that's just figure 3.9. So I think on the left is Yeah, yeah. On the left is the strong kind of nonlinear trend, and on the right is the kind of linear trend. And so yeah, I think
So
that. Oh, sorry.
what you've got is like on the right is if you do a quadratic fit, right? So if you allow the model to understand some nonlinearity, then you get, in this case, like, I don't know if it's saying that the residuals are better, but they're definitely not like as funky as the ones on the left.
I see, yeah. Yeah, and so I guess that's one of the, you can either change the parameters of the model. I think you can also transform the predictors, like you can do a log transformation, like if maybe you have a, your predictors are on like a, not your like your raw data is like on an exponential scale. You could log it to try to make it more linear. But yeah, so there are different ways of dealing with that, I guess. But
yeah, let me get back to the presentation.
Well, I'm now aware that all my pictures, I guess, probably won't be working, but
summer.
so,
Oh, because this is a code output. I get, yeah, that's it. So this is a cell output that it's rendered, which I've got in the file, but I don't have the images. So
I see. Yeah, so you could just easily kind of make these residual plots with the output of this model.fit object. And I'm sure, I think whatever, library you're using to fit your models probably is going to give you some means to do that. But that was one of the lab exercises. And so the next one, and sorry, now I'm having some screen flickering, so I don't know if
we don't have the image for the
okay. I don't know why my everything is just kind of going haywire today. But yeah, so the correlation of the error term is another bad thing that can happen, I guess, linear models. And I think I find the intuition easy to understand, but if anyone has like a more like meaty, mathy kind of way to think about it, I'd be interested. Is, basically if your error terms are correlated, that means that you have less information than your number of observations would imply. And so you can imagine, I think the book gives, an example of like, children from the same family. If you're studying, what do they have? Heights, or like children from the same classroom in a school or whatever. There's like a grouping structure that is not represented in your model, and so you actually have like less information than whatever your raw number of observations would kind of suggest. So your standard errors are going to be way too small to account for that. And I think maybe it's on the next slide. Yeah, and so I thought maybe people would be interested in puzzling over this with me a little bit, is like how to think about this in like a more of a mathematical way. But I think that's right. Like basically, the formula for variance has n in it, and your n can be, you don't want to be dividing by too large of an n, or else your variance is going to be too small. And then the book image in figure 3.10 has three residual plots showing sort of like different degrees of correlated error terms. And so there's one in particular where the error terms are like quite correlated, like the adjacent error terms are quite likely to be similar, and so that's bad. And as far as I could see, like the book didn't really, at this point, we don't have ways to address that. I think you can make various adjustments to the predictors to try to like force you know, you can try to like force them to not be correlated basically, but that's like a transformation you're applying on top of the predictors.
Yeah, I think in kind of like the real world, if you've got like very correlated predictors, you want to get rid of some of them. Or you want to like, yeah, you're going to reduce dimensions. So you do something like a PCA, which is going to get like, you're going to get like a different variable out, but it's going to be like a linear combination of those, and you're not going to have correlation. But I guess that comes a lot later in the book.
Yeah, that makes sense. Yeah, that's a good idea.
In figure 310, is looking at, is that the one about time series data?
Yeah, the kind of auto-correlated time series.
It makes me think there that you've not captured something in your model. If you're seeing that correlation in your residuals, your model isn't accounting for some correlation. I think so. I think that's why they don't suggest fixes, because it might be a bit time series specific.
Oh, so yeah, if you've got correlation of the residuals, yeah, not of the features. Yeah, our predictors, completely different thing.
Oh, right. Okay. Yep. I missed. Yep.
I guess the idea with the time series stuff, it's like the things you're putting in are not independent events anymore, right? So you're violating other assumptions as well.
It's like, yeah, like you've made like a Markovian assumption in your model where every day will be independent, like you're saying, Jack, but then if your residuals are showing that correlation, it suggests that you need to, you know, like AR1 models where you take in the previous 1 day or 2 days or whatever, and see whether you can reduce that correlation in the time series residuals.
Yeah, like you stationarize the stuff, or you remove any correlations, try to get rid of the effects. Like if month is having a big effect and stuff's correlating in a month, well, you try to take out the effect of the month, and then you're just left with like the non-correlated data.
Yeah, and I guess now that I'm thinking about it, like I guess this is the place for like a hierarchical model that like if your correlation is because of some grouping that's like a time unit or like a family unit or class unit or whatever, you can just incorporate that into the model, and then you'll have a better model.
Yeah, it's assumed that there's no kind of pattern in your residuals, right? So if you are finding a pattern in your residuals, then it's like it's bad times.
Yeah.
It's good times because you get to think about what you've missed.
Well, if there were no patterns in the residuals, then they wouldn't need, data scientists. Everything would just be plug and play. Yeah, so the next one is related. It's about the heteroscedasticity of the error term. So and so that's figure 3.11. And then I wrote out an equation that I always found like helpful to help me conceptualize it. But just like if you think of a linear model as just the outcome is just normally distributed according to the mean, which is like beta x, and then sigma. The sort of standard OLS model, the sigma, has no subscript. It carries for every observation, and when you have heteroscedasticity, you have a subscript on sigma. So that's just a different model. So if you're using regular OLS, you can't do that. And I think that's maybe two slides down.
This one?
Well, unless maybe I'm
not seeing any change in your screen there, Jack.
Oh, maybe it's
I've been changing on speaker notes because I wanted to see what slides were coming next, and that's obviously switched up with the Quarto presentation. So okay, let me just stop sharing, go back to this. So were you on this slide?
Yeah, I was yeah, and so this was
Yeah,
this
I was
is
on
like
this slide
trivial,
as
I
well.
guess. Okay, all right.
You
Well,
go.
yeah, but I mean that's kind of trivial, but like you could just see there are two different models. One, one has a subscript on sigma and one doesn't. And if you're doing, regular OLS, which doesn't have a subscript, then you're in trouble if you're not modeling that that variation in your residuals. So yeah, and the next two, and I can't remember what I have on these slides. I think just just outliers and high leverage points are related. Oh yeah, robust standard errors, I guess. And sorry, I have this like screen flickering, so I'm just kind of going off like my memory of what's on the slides. I have no idea what's I don't know. I feel like my computer works fine until it doesn't. But yeah, so I think we didn't cover it in this chapter, but robust standard errors are a way to address heteroscedasticity, although they don't work in every case.
Yeah, I'd say practically speaking, like if you find the pattern in the residuals, it's like, okay, now I need to add a new feature to my model. Like I want to do something. I want to figure out why that pattern's happening, and then I want to add, like via feature engineering, extra information in a predictor that helps me like tackle that part of the data. Or yeah, you want to figure out like, is there actually just a problem in the data, and do you fix it by removing stuff? I think there was outliers and stuff that's here.
Yeah. And yeah, I mean the outliers and the leverage points are kind of, a little trivial, but so the outlier represents like an extreme outcome. A leverage point represents like an extreme value on a predictor. And in each case, they can have pretty large effects on the model. And so there are different ways to like visualize them. And then I think it's like kind of a substantive decision whether or not you want to get rid of them. I think if you think they are due to like maybe an error, like a coding error, or like some kind of like data collection error, then probably they're worth getting rid of. If you think they're like kind of substantively important, then maybe not. So yeah, I think there's room for kind of judgment there a little bit, but
do you define an outlier as something my model predicts badly, or is it like an actual outlier, like not created from the same distribution? Measuring error, get rid of. I think most people tend to go with my model predicts it badly, so it's an outlier rather than like the true meaning.
Yeah, but yeah, I think, and maybe that's another case too, where when you see it, it's like a warning sign that something has gone awry, or a potential warning. Use like maybe usually to me, I'm like, oh, okay, like the data has gotten messed up somehow. Some transformation of the raw data has created an outlier. And so I try to fix that. But yeah, sometimes it could be substantive. I know there's like a famous study of like kind of the use of outliers in the 2000 US presidential election between George Bush and Al Gore, where like some districts in Florida had these kind of wonky ballots that caused them to like sort of vote like way out of step with what we would have predicted them to vote. And so that was a case where you could use outliers to diagnose the fact that something was kind of awry. And in that case, it was like the wonky ballots. But yeah, so, and I think, and I guess I'm worried of the time, but yeah, I think the rest of the slides are about like more of the mechanics of just incorporating interaction terms, polynomial terms into your linear model. So I mean, it's pretty easy, and it will be like, I guess, package dependent. But in this case, like just there's syntax in this fit transform method to add polynomial terms and interaction terms.
Let me see if I get to the. Okay, here is this slide. This was the slide, Cory?
Yeah, that's it. And it just, you can see like, so this is for categorical variables. Sorry, I forgot about these categorical variables. But in any case, categorical interaction or polynomial, like this this function has this nice kind of way of encoding the variables into a nice model matrix for you. So in categorical, it creates dummy variables.
The polynomial are actually very difficult to grasp because it's not really polynomial. They do some kind of polynomial and after they do some derotation, so everything is independent. Because I'm still struggling with a polynomial. It's just not, it's not polynomial. It's polynomial plus some kind of reduction of dimension. So yeah.
Yeah, I don't have like a good response to that. I think, the only comment I have on the polynomial is that I think in some materials I've seen that like maybe like spline terms have become favored over polynomial terms. I don't have like the mathematical basis for that, but I that's kind of something that I've heard. Yeah, I don't know if anyone else has any thoughts on the polynomial.
I think no thoughts that will be useful or be quick enough.
Right. Yeah.
That we wouldn't come in too much over time. I've got a dash. I have to get to a run meet.
Oh.
So